Welcome to DAR Tutors. Today, we're going to explore the fundamental principles of hypothesis testing. Hypothesis testing is a powerful statistical tool for making decisions about populations based on sample data. By the end of this video, you will be able to, first, formulate statistical hypotheses for a z-test. Second, understand the two types of errors that can occur in hypothesis testing: Type 1 and Type 2 errors. Third, and most importantly, perform a complete z-test to make a decision about a population mean. This involves calculating a test statistic and a p-value. And fourth, use critical values and regions as an alternative method to perform a z-test. Let's begin. We often encounter claims about population parameters, like a manufacturer claiming their insect repellent is effective for longer than 6 hours on average, or a doctor claiming a new drug lowers blood pressure more than an existing one. These claims form the basis of our statistical inquiry. In hypothesis testing, we translate these real-world claims into formal mathematical statements. The first step is always to formulate statistical hypotheses. We begin with a null hypothesis, denoted as H0, which represents the status quo or the claim of no effect or no change. The null hypothesis always states that the population mean, mu, is equal to a specific value, mu0. For instance, in the insect repellent example, H0 would be that the new repellent is effective for the same 6 hours as the old one. We operate under the assumption that this null hypothesis is true, and we only reject it if we find overwhelming evidence to the contrary from our sample data. This brings us to the alternative hypothesis, H1. The alternative hypothesis describes what we will accept if we have to reject the null hypothesis. The alternative hypothesis can take 3 forms, depending on what we are trying to prove. If a researcher wants evidence that a new product is superior, they would formulate a greater than alternative. H1, mu is greater than mu0. This is a one-tailed hypothesis. Similarly, if they want evidence that it is inferior, they would formulate a less than alternative. H1, mu is less than mu0. This is also a one-tailed hypothesis. Finally, if a researcher is interested in any change at all, whether it's an increase or a decrease, they would use a not equal to alternative. H1, mu is not equal to mu0. This is known as a two-tailed hypothesis. So, to recap, the first crucial step is to define your null hypothesis as mu equals a specific value, and your alternative hypothesis based on whether you are looking for an increase, a decrease, or any change. Whenever we make a decision in hypothesis testing, there's a possibility of making a mistake. These mistakes are categorized into 2 types: Type 1 and Type 2 errors. A Type 1 error occurs when we make the mistake of rejecting the null hypothesis H0 when it was actually true. This is essentially a false positive. Imagine a court of law. The null hypothesis is that the person on trial is innocent. A Type 1 error would be finding an innocent person guilty. On the other hand, a Type 2 error occurs when we make the mistake of accepting the null hypothesis H0 when it was actually false. This is a false negative. Using the same courtroom analogy, a Type 2 error would be finding a guilty person not guilty. The probability of making a Type 1 error is very important, and it has a special name. The probability of a Type 1 error is called the significance level, and it's denoted by the Greek letter alpha. A common significance level used in science is alpha equals 0.05. This means we are willing to accept a 5% risk of incorrectly rejecting a true null hypothesis. In other words, there's a 1 in 20 chance our decision to reject H0 might be wrong. It's a trade-off. By choosing a very small significance level, we reduce the chance of a Type 1 error, but we increase the chance of a Type 2 error. We'll explore this trade-off in an investigation later. Now let's apply these ideas to the z-test for the mean of a population. The z-test is specifically designed to test hypotheses about a population mean, mu, under certain conditions. First, we must know the population variance, sigma squared. And second, the population itself must be normally distributed. If the population isn't normal, but our sample size is large enough, say greater than 30, we can use the central limit theorem to proceed as if the sample means are normally distributed. The core of the z-test lies in its test statistic. This statistic measures how many standard errors our sample mean, x bar, is away from the null hypothesis mean, mu naught. Under the null hypothesis that mu equals mu naught, the sample mean x bar follows a normal distribution with mean mu naught and variance sigma squared over n. To calculate how far our sample mean is from the hypothesized mean, we standardize x bar to form the z statistic. We find the observed value z by plugging in our specific sample mean x bar. The key is that this z statistic follows a standard normal distribution, n of 0, 1. This standardization allows us to compare our test result to a universal standard normal distribution to determine how probable it is. In essence, the z statistic tells us if our sample mean is close enough to the null mean or if it's extreme. We're going to dive into the second step of our hypothesis test, choosing a significance level. We've talked about it conceptually, but now let's see how it's applied. The significance level, alpha, is a predefined threshold that determines how strong our evidence must be to reject the null hypothesis. It represents the probability of committing a type 1 error. A crucial point, often emphasized in the IB curriculum, is that this decision must be made before you calculate your results. If you calculate a p-value first and then choose an alpha to get the outcome you want, you are manipulating the test and committing a statistical fallacy. There is no single correct significance level. The choice of alpha depends entirely on the context of your problem. You must justify your choice. Let's look at a few examples. For a simple survey or a market research study where the stakes are relatively low, a significance level of 0.1 or 10% might be acceptable. This is a more lenient test, allowing for a higher risk of error. However, for a scientific study, especially in fields like biology or psychology, the standard and most commonly accepted significance level is 0.05 or 5%. This means the researchers are willing to accept a 1 in 20 chance of being wrong. In critical applications, such as medical trials for a new drug, the consequences of a type 1 error are severe. A type 1 error here means concluding a drug is effective when it isn't, potentially risking patient safety. Therefore, a much stricter significance level, like 0.01 or even 0.001, is required. This drastically reduces the risk of a false positive. To summarize, the significance level alpha is the probability threshold you set for your test, and it must be determined before analysis, based on the real-world implications of a type 1 error. We've formulated our hypotheses, H0 and H1. We've chosen our significance level alpha. Now, the next crucial step is to gather data and calculate a p-value. Let's perform a z-test to see this in action. Consider a problem from your notes. Exercise 30B, number 3. The problem asks us to perform a hypothesis test at the 5% level of significance to determine if a customer's claim is valid. The claim is that bags of salted cashew nuts, labeled 100 grams, are actually lighter. We know the standard deviation of the population is 1.6 grams. A quality control manager samples 40 bags and finds the mean weight is 99.4 grams. First, the hypotheses. The customer's claim that bags are lighter translates to the alternative hypothesis. H1, mu is less than 100. This is a one-tailed test. The null hypothesis, H0, is that the mean weight is as stated mu equals 100. Step 2 is to state the significance level alpha. The problem specifies a 5-byte significance level, so alpha equals 0.5. Now for step 3, we calculate the observed test statistic z. The formula is x bar minus mu naught, divided by sigma over the square root of n. Plugging in our values, 99.4 minus 100 divided by 1.6 over the square root of 40. This gives us approximately negative 2.37. For step 4, we calculate the p-value. This is the probability of observing our test statistic, 237, or something even more extreme, assuming the null hypothesis is true. Since our H1 is less than, we are looking at the lower tail of the standard normal distribution. You would use your GDC's normal CDF function to find the area to the left of 2.37. The calculator gives a p-value of approximately 0.089. So far, we have our p-value. Now we move on to the final steps of making a decision and interpreting the result. The decision rule is simple and applies to all hypothesis tests. We compare our calculated p-value to the significance level, alpha. If the p-value is less than or equal to alpha, we reject the null hypothesis H0. If the p-value is greater than alpha, we accept H0. Let's be very clear here. We don't say prove H1 or prove H0. We either reject or accept the null hypothesis based on the strength of our evidence. Returning to our cashew nut problem, we found a p-value of 0.0089 and our significance level was 0.5. Is the p-value less than alpha? Yes, 0.0089 is less than 0.05. This means that the probability of observing our sample mean of 99.4 grams, or something lighter, if the bags truly contained 100 grams on average, is less than 1%. This is a very small probability, which suggests our observation is unlikely to have happened by chance if H0 were true. Since we reject the null hypothesis H0, we accept the alternative hypothesis H1. Now for the final step, we must interpret our decision in the context of the original problem. We state our conclusion in a clear sentence. Our conclusion is, at a 5% level of significance, there is sufficient evidence to support the customer's claim that the mean weight of the cashew bags is less than 100 grams. This means the factory manager should investigate further. This completes the full p-value method for a one-tailed z-test. The p-value method is the most common way to perform a hypothesis test, but there is an equally valid alternative method that is useful for understanding the test structure, the critical value method. The critical region is the set of all possible test statistic values that would lead us to reject the null hypothesis. The boundary of this region is defined by the critical value, which we'll call C. The critical value, C, is the value of the test statistic that marks the boundary of the critical region. Its p-value is exactly equal to our significance level, alpha. Let's revisit the cashew nut example with this new method. We are performing a one-tailed test with H1 being mu less than 100 and alpha is 0.05. Since H1 is less than, our critical region will be in the lower or left tail of the standard normal distribution. We need to find the critical value C, such that the area to its left is 0.05. You can find this using the inverse normal function on your GDC. For an area of 0.05, a mean of 0, and a standard deviation of 1, the calculator gives us a critical value of approximately 1.64. This means our critical region is any z-value less than or equal to 1.64. If our calculated test statistic z falls into this region, we reject H0. Otherwise, we accept it. Recall that our calculated test statistic for the cashew nuts was approximately 2.37. Does 2.37 fall into the critical region? Is 2.37 less than or equal to 1.64? Yes, it does. Since our z-value is less than the critical value, we reject H0. We reach the exact same conclusion as with the p-value method, as they are two sides of the same coin. So far, we've focused on one-tailed tests. Now, let's look at the two-tailed test, which we use when we're testing for any change, whether it's an increase or a decrease. In a two-tailed test, our alternative hypothesis, H1, is that the population mean is not equal to mu0. Since the change could be in either direction, we split our significance level alpha between the two tails of the null distribution. For example, if we have a farcent significance level, 2.5% will be in the lower tail and 2.5% in the upper tail. This means there are two critical values, a negative one and a positive one, which are symmetric about the mean. These critical values define the critical region, where a test statistic falling into either tail will lead to rejecting H0. The decision rule also adapts. If we're using the p-value method, the p-value is calculated as 2 times the probability of our test statistic being more extreme in the relevant direction. This accounts for both tails. Let's work through an example. Suppose we want to test if the mean daily energy intake of students at a school has changed. The historical mean is 92110 kilojoules, and the standard deviation is 300. A sample of 50 students this year has a mean intake of 9,100 kilojoules. We'll test this at a 2% significance level. First, we calculate the test statistic z, which is negative 2.59. Since this is a two-tailed test, the p-value is twice the area in the tail corresponding to our negative z. So 2 times the probability of z being less than or equal to 2.59. This gives us a p-value of approximately 0.8096. Now we compare our p-value of 0.096 to our significance level alpha of 0.02. Since 0.5096 is less than 0.2, we reject H0. This means there is significant evidence at the 2% level to conclude that the mean energy intake has indeed changed from 90 to 10 kilojoules. Let's pause and consider some of the theoretical implications of what we're doing. This involves the theory of knowledge. The whole framework of modern statistics owes a great deal to Sir Ronald Fisher, who is often called the father of modern statistics. He established the practice of using a significance level of 0.05. He stated that a p-value of 0.05, or 1 in 20, is a convenient point to judge whether a deviation is significant. Notice the words convenient and judging. Fisher himself did not see this as an absolute rigid rule. This highlights the human element in science. The choice of 0.05 is a convention, a shared standard. But as we discussed, the correct alpha should be determined by the context and the consequences of an error. This brings up a fascinating question about confidence. If a researcher reports a finding with 95% confidence, do we automatically stop to think about the 5% chance they are wrong? For something trivial, probably not. But for a medical treatment? Absolutely. It is the researcher's responsibility to clearly state their confidence level and the associated risks. Now, let's explore a dangerous pitfall in statistics called the multiple testing problem. This can lead to misleading and even false findings. It's often illustrated by the famous XKCD comic Jelly Beans Cause Acne. The comic starts with a claim. Jelly beans cause acne. A scientist tests this with a two-tailed hypothesis at a 5-pot significance level. They find no link and are about to go play Minecraft, but the claim maker insists, "I hear it's only a certain color that causes it." The scientist, perhaps unethically, decides to perform not just one, but 20 separate independent z-tests. One for each color of jelly bean. Let's think about this. Each of these 20 tests is run at a 5% significance level. This means that for each individual test, there is a 5% chance of finding a significant result and rejecting the null hypothesis, even if it is true. This is our type 1 error probability. The probability of getting at least one type 1 error across all 20 tests is much higher. The probability of not getting any type 1 error is 0.95 to the power of 20, which is about 0.358. So, the probability of getting at least one type 1 error is 1 minus that, which is over 64%. Sure enough, in the comic, the test on green jelly beans comes back significant, with a p-value less than 0.05. The result is immediately picked up by the news, which announces a definitive link between green jelly beans and acne with 95% confidence. The public is deceived because the news fails to report that 19 other jelly bean colors were tested with no significant results. This is a classic example of how multiple testing can be abused to create spurious findings. Hello, I hope this video on hypothesis testing has been helpful. We've covered a lot of ground today, from setting up hypotheses and understanding error types to performing z-tests using both p-values and critical values. Mastering these concepts is key to success in your IB/AI/HL exams. If you're looking for more personalized support, expert guidance, and exam-focused strategies, contact DAR Tutors today. We offer online and home tuition for IB A-Level and IGCSE. Our experienced tutors can help you navigate complex topics, refine your problem-solving skills, and build the confidence you need to achieve your academic goals. Now let's put your knowledge to the test. Here are 5 IB-style practice questions that cover the concepts we've discussed. Pause the video and try to solve them on your own. Afterwards, we will go through the fully worked solutions. Here is question 1. Here is the solution to question 1. First, the hypotheses. The manager is testing if the mean volume is 250 milliliters or less, so the alternative hypothesis is mu is less than or equal to 250. However, for a test, we always use a strict inequality for H1, and an equality for H naught. So H naught is mu equals 250, and H1 is mu is less than 250. The significance level is given as 5%, so alpha is 0.05. Now we calculate the observed test statistic Z. Plugging in the sample mean of 246, the hypothesized mean of 250, the standard deviation of 10, and the sample size of 25, we get Z equals -2. Since H1 is less than, this is a one-tailed test in the lower tail. The p-value is the probability that Z is less than or equal to 2. Using the normal CDF function on a GDC, we find this probability is approximately 0.02. Finally, we compare the p-value to alpha. Our p-value of 0.00228 is less than alpha, which is 0.05. Therefore, we reject the null hypothesis. The conclusion is that there is sufficient evidence at the 5% significance level to suggest that the machine is dispensing less than the stated 250 milliradians. Here is question 2. Here is the solution to question 2. The consumer group believes the claim is incorrect, which implies they are interested in any deviation from 480 km/h, either higher or lower. This is a two-tailed test. So H naught is mu equals 480, and H1 is mu is not equal to 480. The significance level is 1%, which is alpha equals 0.01. Calculating the test statistic Z using the sample mean of 474, the hypothesized mean of 480, the standard deviation of 15, and a sample size of 36, we get Z equals -2.4. Since H1 is not equal to, this is a two-tailed test. The p-value is 2 times the probability that Z is less than or equal to -2.4. Using a GDC, this is approximately 2 times 0.0082, which equals 0.0164. Now we compare. The p-value of 0.0164 is greater than alpha, which is 0.01. Because the p-value is larger, we accept the null hypothesis. The conclusion is that at the percent significance level, there is insufficient evidence to dispute the manufacturer's claim. Although the sample mean was lower, the deviation was not extreme enough for us to be confident it wasn't just due to random sampling. Here is question 3. Here's the solution to question 3. The sociologist is testing for an increase in mean height. This indicates a one-tailed test with a greater than alternative hypothesis. So H naught is mu equals 170, and H1 is mu is greater than 170. The significance level is 5%, so alpha equals 0.05. The test statistic Z is calculated as 177 minus 175, divided by 8 over the square root of 4. This simplifies to 2 divided by 1, which gives Z equals 2. Since H1 is greater than, the p-value is the probability that Z is greater than or equal to 2. Using a GDC's normal CDF function, this probability is found to be approximately 0.0228. Comparing the p-value to alpha, we see that 0.0228 is less than 0.05. We reject H naught. The conclusion is that at a 5% significance level, there is sufficient evidence to suggest that the mean height of adult males has increased beyond 175 centimeters. The observed sample mean was high enough to be statistically significant. Here is question 4. Here is the solution to question 4, using the critical value method as requested. We are looking for a change in the defect rate, not a specific increase or decrease. This means it's a two-tailed test. H naught is mu equals 10, and H1 is mu is not equal to 10. The significance level is 10%, so alpha equals 0.1. Using the critical value method, we must find the critical values that correspond to this alpha level for a two-tailed test. This means we split the 10% significance between the two tails. Each tail will have an area of alpha over 2, which is 0.05. We need to find the z-scores that have 0.05 probability in the lower tail and 0.05 in the upper tail. Using the inverse normal function, the critical values are found to be positive and negative, 0.64. This defines our critical region. Now we calculate our observed test statistic Z from the sample, It's 9.7 minus 10 divided by 1.5 over the square root of 100. This gives us z equals -2. Finally, we compare our observed z value to the critical region. Our z value of Chi2 is less than the lower critical value of 1.64. Since our test statistic falls within the critical region, we reject the null hypothesis. The conclusion is that there is sufficient evidence at the 10% significance level to say that the new process has caused a significant change in the defect rate. Here is question 5. Here is the solution to question 5. This time, we'll find the acceptance region. The question asks if the new technique has increased the breaking strength, which means we are looking for evidence that the mean is greater than 500. This is a one-tailed test. So H0 is mu equals 500 and H1 is mu is greater than 500. The significance level is 2.5%, so alpha equals 0.025. We need to find the critical value C, such that the area to its right is 0.025. This means the area to its left is 1 minus 0.025, which is 0.975. Using the inverse normal function for an area of 0.975, we find the critical value C is approximately 1.96. The critical region is for any z-score greater than or equal to 1.96. The acceptance region, then, is everything else. The acceptance region is the set of all z-scores less than 1.96. Now let's calculate our observed test statistic for the sample. The sample mean is 512, the hypothesized mean is 500, the standard deviation is 25, and the sample size is 20. This gives us a z-value of approximately 2.15. We check if our observed z-value falls into the acceptance region. Is 2.15 less than 1.96? No, it is not. In fact, 2.15 falls into the critical region, outside of the acceptance region. Therefore, we reject the null hypothesis. The conclusion is that at a 2.5% significance level, there is sufficient evidence to claim that the new manufacturing technique has increased the mean breaking strength of the rope. Thank you for joining this DAR Tutor session on hypothesis testing. You've worked through the entire process, from setting up hypotheses to making conclusions. You're now well-equipped to tackle z-test problems in your IB/AI/HL studies. Remember to review these key steps. State H0 and H1, choose your alpha, calculate your test statistic and p-value, compare them, and write a clear conclusion in context. Stay focused, practice regularly, and don't hesitate to reach out for more help. Until next time, keep learning with DAR Tutors.